Hello students, welcome back to the control system class. In the earlier few classes, we were doing block diagram reduction. That is, we found out the transfer function of a given control system using block diagram reduction technique. In the next few classes, we will be focusing on signal flow graph. The signal flow graph is also a technique to compute the transfer function, but compared to block diagram reduction technique, the signal flow graph is slightly easier because the effort needed to compute the transfer function is lesser in signal flow graph. So the next few sessions we will be focusing on how to find transfer function of a system using signal flow graph. Let us get into the session today. Signal flow graphs are a graphical representation of control systems. So here's a definition for signal flow graph. It depicts the flow of signals from one point to another in the system, and it also gives the relationship among the signals flowing in the system. Similar to block diagram technique, signal flow graphs are also used to compute the transfer function of the system. But the only difference is here in a signal flow graph, you have a direct formula to calculate the transfer function of the system. Whereas in block diagram, you have to go through many steps to compute the transfer function. So here you've got a formula called Mason's gain formula. Using this formula, we will be able to calculate the transfer function of signal flow graph directly. This formula is named after the person who developed a signal flow graph by name S.J. Mason. We can obtain a signal flow graph from the block diagram as well as from algebraic equations defining the system. Algebraic equations, I mean that the frequency domain equations. So this part will be dealt in the fifth unit, that is how to draw signal flow graph from the equations defining the system. Whereas the scope of the first unit is lying in this point, that is you will be able to draw the signal flow graph from the block diagram and then use Mason's gain formula to obtain the transfer function of the system. And this signal flow graph has a restriction that it is applied only to linear systems. It cannot accommodate non-linear systems. This slide gives you an example for signal flow graph. This is a simple example for signal flow graph. Whatever you see here, these lines are called as branches. So a line segment connecting two nodes are called as branches, and what you write on top of that branch is called as gain of that particular branch. So these dots are called as nodes. The points where two or more branches connect together, those points are called as nodes, and they represent a signal, and you give a name for it, a variable name for representing the signal at this point. So here y1 starts to flow at this node, and the signal at this point is named y2, that variable name is y2. Similarly, this node is named y3. That means that the signal at this point is named by the variable y3. So you've got input node. Input node is a node which will have only the outgoing branches. You can see that this input node has only outgoing branch. And there is a output node which will be at the last of the signal flow graph. This will have only incoming branches. Whereas mixed nodes in between the input node and the output node, these nodes will have both incoming and outgoing branches. So putting all the points together, the signal enters into the input node. It flows like this, and you've got a tapping of signal at this point and getting fed back through a branch called with a gain minus D. And these A, B, C are gains of each and every individual branch. So this is a simple signal flow graph. So there are certain terminologies which we should know before we enter into reducing the signal flow graph. First thing is forward path. Forward path is nothing but you should take a path from input node to the output node such that you don't cross a node more than once. That is here, this is the forward path. This is the forward path. We are not covering a node more than once. So such a path is called as a forward path. It should lead to the output. From the input, the path should lead to the output. That is called as forward path. A loop is nothing but, so you can see here, this thing is a loop where the output has to go to the input and you should form a closed loop. Okay, this is your feedback loop. Okay, and gain of this particular loop will be calculated by multiplying the gains of the individual branches. So there are how many branches involved in this loop? This is one branch and this is another branch. The gain of this branch is b and this gain of this branch is minus d. So the path gain of this loop is, I repeat it, the path gain of this loop is minus b into d, minus of b into d. So the path gain of this forward path will be, for example, if this is a forward path and the path gain of it will be a into b into c. That is, you have to product the gains which you traverse through. Okay, this forward path is from this point to this point and you've got a b c are the gains that we travel through. So it is the product of all the gains that we travel through. That is called as forward path gain. There is something called self loop. Suppose if you have a loop like this which starts in the same one node and ends in the same node. If you have got a loop like this, it is called a self loop. Starts at one node and ends in the same node. To sum up, we have seen the terminologies like forward path gain, loop, loop gain, and self loop. So all these things you will see in the next slide, the definitions of it. One more point is, if we are going to have uh, two loops, for example, just let us draw a bigger signal flow graph. If two loops are there in the signal flow graph, they are called non-touching loops when they don't share a common node. For example, if you are going to have a loop here, these two loops can be non-touching if they don't share a common node. If I draw a loop here, that loop and this loop does not share a common node. So you can call it as a non-touching loop. If I draw another loop like this here, okay, then these two loops will not come under the category of non-touching loops. So the another term, non-touching loops. So the definitions are here. Students can go through it after the completion of this video. So here is a small exercise that we will do so that you get better understanding of all the terminologies. So this is a signal flow graph given. This x1, x2, x3, x4, x5, x6 are names of the nodes or names of the signals at that point. And this A12, A23, A34 are gain of this individual branches. Okay, individual branches. So now let's start. So which is the input node? This particular x1 is the input node. Which is the output node? Output node is x6 is the output node. How many forward paths are there in this? So let's start with the input and see how many forward paths are there. I am able to see one forward path from the input to the output. You know that the forward path should lead to the output node. So this is one forward path. Look for any other forward path here. Okay, I can see another forward path where I come to this node. I take a path like this and go like this. So there are two forward paths. So you cannot take this path as this path like this as a forward path, because when you do that, this node will be covered two times. Okay, every node should be covered, or node should be covered only once. Okay, skipping a node is not a problem, but the node should be covered only once. So this path cannot be taken as a forward path coming like this. going like this, coming back and going out. So this will not be considered as a forward path. There are only two forward paths here now. One fellow is this fellow, and the second one is coming here, taking this path and going out. Okay, this is another second forward path. These are all feedbacks. Okay, I cannot move like this, come back and then go out. Okay, so that means that I cover these two nodes two times, so that is not allowed. So there are only two forward paths. How many loops are there? How many loops are there? Let's find how many loops are there. This is one loop, this is another loop, second loop, third loop is this fellow. No, this is not a loop. Actually, it's not coming back. Am I right? So this fellow is not a loop. Coming like this, going. No, I'm not able to go. So this is not a loop. So this is one loop. This is second loop, and this is third loop. This can be considered as a loop. Okay, this is a loop. So one, two, and three. Three loops. So gain of every loop will be A23 into A32 will be the gain of this loop. A34 into A43 will be the gain of this loop. And just A44 will be the gain of this loop. And the gain of forward paths will be, I told you that you should multiply all the gains that you traverse through. So here it is a multiplication of, for this first forward path, the path gain is A12 into A23 into A34 into A45 into A56. Whereas the path gain for the second path is A12 into A23 into A35 into A56. So that will be the path gain of second path. So now we are going to see, is there any set of non-touching loops. So there are only three loops here. This loop and this loop touches at this point. This loop and this loop touches at this point. So there is one pair, that is this loop and this loop does not touch each other. Okay, this loop and this loop does not touch each other. So this becomes a pair of non-touching loop. So I think we have answered all these questions: input node, output node, two forward paths, and gains of the forward paths, loops, gains of the loops, and how many non-touching loops. So this is the only pair which is non-touching. So this particular slide will tell you how to convert a given block diagram to a signal flow graph. Okay. So first thing that you have to do is take the input point as one node. Take the output node as another point here. Okay. And wherever you see intersection of many branches at one point, you take that as a single point here and name and give you a name by x1, x2, x3, so on. So here I can see there is a point here where many people are coming and meeting. Okay, this fellow, this fellow, this fellow, and this outgoing fellow, all are getting are meeting at this point. So I will give a node for this particular point, and then I will look for any other point where many people are meeting. So here is a point where this fellow comes and meets, and this arrow mark also comes and meets here. And from the same point, that is from here, there is a output, and that point you tap a output. So I will make this as one point. Okay, if required, but in this diagram I have not made another point by name x3 or x4, but you can take this particular point as another node and connect between this node and this node and say that the gain between them is 1. So that is possible, but we have taken these two combinedly to one node. You can see here it is x2. Okay, and then here you can see that there is a interconnection, so I take that as x3, and this simple point I have taken here, just name it as x4, right? Can name it as x4. Now let us see from which place to which place the gains are there. So between x1 and x2 it is g1. From x2 to this point it is minus h1. See, since it is negative feedback, we are going to write h1, that is minus h1. Okay, and what else? From this point x3 you got to move to this x1 with minus h2 because it's negative feedback, so it is minus h2. And from this point you go back to this x2, okay, through minus h3. Okay, and is there any gain from this point to the output node? No, so simply write it as 1. Okay, and from this point to this point also there is no gain, so I write it as 1. But from this point to this point I have a gain g1, so I write it on top of this particular branch, that gain is g1. Okay, so that's why I said even if you're going to make a small change here by introducing another node, okay, another node here representing this point, and if you give a unity gain, that is also correct. Okay, so you can have another point saying that, so this is also a meeting point, so I will give another node. Fine, you can take it. This will be one node where h3 comes and meets, and there will be another node. Okay, from that node you can go to this x3. So from this node if you go to x3, the gain will be g2 there, but you will have another node inserted with gain 1, that is one for this point, another one for this point. So in between there is no gain, so I will write it as 1. So this particular signal flow graph can be slightly modified, and you can put another node here and say that the gain between that node and this node is 1. Or else, since you don't have anything in between this summing point and this branching point, you take it as a single point. That is, I tap a signal from this point, and I also bring a feedback to this point, and there is a incoming signal going to this point. Okay, so all are happening at this point, so we have put one single point for this. So students will take some time to understand. Okay, so I will hold this picture for some more time. If you want, I can repeat it also. That is, the intersection points has to be made as nodes. So this is an intersection point, I made it as a node. The starting point R of S, and this is also a meeting point, I made it as x2. uh, I have clubbed these two, so this is a meeting, this is a branching point, so I have made it as a node. And from here something is tapped, so I have made it as a node. Though this point itself is the output, simply we have taken, because from this point we have taken it to C, so I have connected one branch here with unity. So even if you don't have this branch, nothing happens. So at this point itself you can name it as C of S. So that's how you convert a signal flow graph, sorry, block diagram into a signal flow graph. In the next video, we will see how to reduce the signal flow graph to obtain the transfer function. Thank you.